de hoy, porque conocí hace unos meses a Oliver en una visita a la Universidad de Nevada en Las Vegas, y ha sido un placer platicar con él, y hace poco publicó unos artículos muy importantes, muy relevantes, y lo invité a que los compartiera con la comunidad. Oliver es un minerólogo y cristalógrafo que hizo la maestría en la Universidad de Colonia en Alemania, donde igualmente sacó el doctorado. Esto, donde también estuvo trabajando en el Instituto Max Planck de Química en Mainz. Posteriormente realizó una estancia en la Universidad de Carnegie en el laboratorio de geofísico, y fue visitante en Caltech, y poco después se incorporó al departamento de Geosciencias de la Universidad de Nevada. Oliver es un mineralólogo y cristalógrafo, con especial interés en minerales de alta presión, su ocurrencia, su química cristalina, así como su impacto en la geoquímica del manto de la Tierra. Sus herramientas son principalmente basadas en difracción de rayos X y espectroscopía de sincrotrón a nivel de microescala. Y el seminario que nos va a hablar hoy es Diamonds, Lower Mantle and the Carbon and Water Cycle. So, Oliver.
Gracias, Pablo. I have to give the talk in English. Frankly, I would even have trouble giving such a talk, a scientific talk in German, because I do not remember many of the technical terms anymore. So anyway, yeah, so I will talk today about diamonds and the relation to the lower mantle and the global carbon and water cycle. So here's a view graph that Science made several years ago after we published an article about ice inclusions in diamond that relates a brilliant cut diamond to the depth of the Earth. And it's also represents one of the tools that we are using, just a diamond anvil cell for experiments where we use two such brilliant cut diamonds where the very tip is polished off. These two anvils are opposed, and a small sample, for instance, ice, water ice, or carbon, is included and pressurized between these tips, and then we can actually measure its change with pressure, with temperature, and etc. Anyway, so I acknowledge the funding agencies here. Much of my experiments, as Pablo already mentioned, are conducted at the synchrotron, so at the Argonne National Lab, at the Advanced Light Source. So without these large facilities, I probably could have done only a small fraction of my work. All right, so I start here with something that all of you know. In fact, many of you know that much better than I do. This is a view graph from my introductory lecture, and it shows what is usually called in earth science the water cycle. However, this water cycle that goes down to a few meters, or let it be tens of meters down in the ground, is not the only water cycle that we have on the Earth. There's a second water cycle that had been unraveled in the last 2 decades of the 20th century. And this is related with subduction. So if you have convergent margins, continent-continent, oceanic-crust subduction zones, sediments, as well as hydrothermally altered oceanic crust, will dehydrate when it's subducted back into the mantle. These hydrous fluids, they rise in the mantle wedge above the subducted slab and cause partial melting, and this gives rise to volcanisms such as island arcs, or the volcanism along the American Cordillera. So this release of water is from water that is chemically bound in minerals that become unstable in the at the pressures and temperatures of the mantle when the slab starts warming up. And some of them actually transform to denser hydrous minerals, such as lawsonite, which is shown here, but they eventually will also break down. So these type of mechanism of recycling of the fluids and incompatible elements that are dissolved in the fluid can be geochemically interpreted, and this is all very well understood nowadays. And so this is the second water cycle that we have on Earth, and it's essential for Earth being a geologically active planet. So when this was all research that was done when I was student or even before I was student, in fact, Ted Green, who was one of the leaders in this research, was a frequent visitor in my department in Cologne University. But nevertheless, at that time, I had learned when I was undergraduate student that the upper mantle of the Earth is bone dry. There's no water beyond that that comes in through subduction, and it's basically immediately released. However, that turned out to be wrong. There's a paper by Dave Bell and George Schwarzman. It was published in the early 1990s, and that showed there's actually not a large, but a noticeable amount of water chemically bound in pyroxenes in mantle peridotite. Olivine, as the main mineral, is comparatively dry. So here's a picture of garnet peridotite, and if you look more carefully, you actually can see the pyroxenes there. So then when I started my PhD thesis work, I think in 1995, I went to a workshop in the Geo Institute in Bayreuth, and Joe Smith gave a talk about a paper that he had published a year ago. Joe Smith is, like me, a mineralogical crystallographer, and he was saying high pressure polymorphs of olivine, watzleite, as well as ringwoodite, shown here. This is watzleite. They can actually chemically dissolve a fairly large amount of water, up to 3% H2O can be chemically dissolved in watzleite. And it's all based on crystal chemistry. So it doesn't mean that there is really that much water in watzleite in the deeper mantle, but it is possible. So the question now is how much water actually is residing in these higher pressure polymorphs of olivine, watzleite, and ringwoodite in the mantle. So before I talk about this, I'll just briefly discuss what actually defines high pressure minerals. So it's a paper that I published a few years ago in American Mineralogist, where I tried to come up with a simple schematics for the effect of pressure on minerals. So I distinguish between low pressure minerals, intermediate pressure minerals, and high pressure minerals. So low pressure minerals in their structure are mostly controlled by changes in their entropy as a result of different temperatures of their formation, and pressure does not play a big role. If pressure is increased, so if we go from the Earth crust, which is not even shown here, to the upper mantle, in terms of pressures, we have changes of structures, and that might be illustrated from, for instance, for the change from quartz to coesite. So the fundamental building unit is still silica tetrahedra. However, they are reconnected to establish a denser network in coesite. If coesite transforms into stishovite, this is a very fundamental change. So the coordination of silicon by oxygen changes from 4 to 6. And actually the chemical bond character changes substantially as well. So the 3D orbitals of silicon, for instance, are involved in that bonding, which is very different from the chemical behavior of silicon at ambient pressure. Then if you look at mantle minerals, such as magnesium orthosilicate, magnesium metasilicate, they undergo similar changes. They go from chain silicates like the pyroxenes, or from sorosilicates like olivine, to spinel type structures like wurtzlite and ringwoodite, and then ultimately they break down into what I define as oxides, so magnesium, metasilicate. In the perovskite structure, bridgmanite is actually an oxide. It's not really a silicate anymore because the bond is much more ionic, the silicon-oxygen bond, than it is at ambient pressure. So we go from nesosilicates, olivine, to sorosilicates, wurtzlite, ringwoodite, and then we go to oxides. So the question is then, how do these structural changes affect the chemistry in the mantle? How does it affect minor and trace element chemistry between upper and lower mantle? And what happens to water that is chemically bound? So people had studied magnesium silicates in very water-rich systems. This is mostly experimental work. The one phase that is known to form in the upper mantle titanoklinikumide I show here, but many of them so far had not been found as minerals. I will show you the one that had been found soon. So this is phases are called alphabet phases. They're not really structurally related, but they are magnesium silicates, sometimes magnesium aluminosilicate, and they can dissolve a lot of water. Now the question is, do they really exist in the mantle? Then if you go to the lower mantle, where we have magnesium silicate oxide bridgmanite and magnesium oxide periclase, it turns out that they're actually very poor solvents of water. So there's very little water. So there's still some people argue with this, but the general consent is that lower mantle minerals dissolve very little water. So overall, this is from 2 papers by Tschauner. We have schematics for the Earth mantle, and its water solubility in the crust is wet. The upper mantle is fairly dry, but not totally dry. And then the transition zone wet, and the lower mantle dry. And then I don't know what Carato wanted to tell us here with this high amount of water in the core. And we talk about oxidation, but we can leave that alone. We are not talking about this. Now, if we have this kind of scheme, wet, dry, upwelling material in the mantle will be affected by this. So if there is subduction, and there is, by momentum conservation, upgoing material related to this convection. So material that from the eventually wet transition zone will rise and will release the water. Or if there's a hot upwelling from the deeper mantle, a plume, this plume material will rise through the transition zone. Again, water-rich material is trapped, and it will release the water. If that happens, and this material goes into the upper mantle where the minerals cannot chemically dissolve that much water, there should be then a fluid or melt-rich layer at the border between the transition zone and the upper mantle. That's a hypothesis. Again, we don't really know how much water there really is in the transition zone. But if there's a lot, then we would maybe have that scenario. And then immediately people, of course, were saying, if you have this, you should see much more volcanism, etc., etc. We will talk about this. All right, so of course, besides crystal chemistry and geochemistry, we also have geophysics. We can interpret seismic wave attenuation in terms of thermal and chemical anomalies. Water-rich material may show characteristic attenuation of seismic waves. So there is a paper that was published by Brandon Schmand and co-workers where they combined experiments in a diamond cell. This is ringwoodite, so magnesium orthosilicate in the spinel structure. So the transition zone mineral that had been zapped with a laser at high pressure, 30 GPa, and transformed into bridgmanite and periclase. And this is this red areas here. Then infrared spectra were collected, and turns out they were dry. So the water that is dissolved in the ringwoodite is released when it transforms into the lower pressure mantle minerals, bridgmanite and periclase. And Brandon then reinterpreted seismic data that were collected around the 660-kilometer boundary between transition zone and lower mantle, in particular from underneath the Americas. And he suggested that these negative anomalies in the shear wave velocities are related to this release of water from the transition of wet transition zone minerals into dry lower mantle minerals. Now that had been debated. There is a very meticulous study by Christine Hauser that was published a few years ago, where she reanalyzed seismic data globally. And her conclusion is that globally, there's actually very little water in the transition zone or the shallow upper mantle. It can go up to a little bit more than 1.28%, which is quite a bit. But overall, for the given statistics, it's somewhere ranging about 0.3 or 0.48%. There's still more than in the upper mantle, but it's much less than what is crystal chemically possible based on Joe Smith data. There's yet something else that we should take into consideration, and that is that pressure, because it changes the chemical behavior of elements, contributes to the water cycle in an unexpected way. There's a pressure-driven disproportionation of ferrous iron into ferric iron and metallic iron. And this is a purely pressure-driven effect. It has to do with the high spin, low spin transition of iron that makes the volume of ferrous iron unfavorably large at elevated pressure and then drives this disproportionation reaction. Arno Rohrbach and Max Schmidt used these results in combination with own experiments to come up with the schematics that ties the carbon cycle with these iron disproportionation process. So they subducted lithosphere that is rich in carbonate and is eventually hydrous, and it goes down to the border between the transition zone and the lower mantle. It will eventually release its content of fluids, and this carbonate and water then will react with the native iron that is there and basically drives that reaction backward by changing the redox conditions. So if that's true, then we have a mechanism that forms diamond through reduction of carbonate and oxidation of iron. And that ties the redox condition in the deeper transition zone and the lower mantle with the recycling of carbon in the depth of the Earth. Okay, again, this is an experiment-supported hypothesis. So what is lacking are data from natural samples. So this is where I started to, and other people as well, started to look into this. So the first paper that seems to support this hypothesis by Schmidt and Rohrbach was published by Evan Smith and collaborators a few years ago. They found gem quality diamond that had inclusion of iron nickel alloy, sulfide, iron carbide. So they concluded that this finding is consistent with this disproportionation reaction that we know to exist, and with this redox freezing melting cycle that ties carbon and iron cycle, and then indirectly the water cycle as well, because if there's carbonate in subducted lithosphere that goes that deep, then there should also be water. In my own experiments, I see iron and iron carbide inclusions quite frequently. So here's an X-ray fluorescence map that was collected with 2 micron spatial resolution on some diamond. you see in 3 colors, RGB, you see, sorry, what is that? Zinc, iron, and nickel. And so there are iron-rich inclusions here. No? So it's actually most of them, if you go to those locations and collect X-ray diffraction data with the same X-ray beam, we see it's actually iron or iron carbide. So there's something to it. Now, the study of minerals from the transition zone on the lower mantle even goes back to before these experimental studies by Rohrbach and Schmidt and by Schmand and Jacobsen. It was Thomas Stachel and co-workers Jeff Harris, Gerhard Brey, who found about 10 years ago that inclusions from some diamonds from South America contain minerals that are surprisingly similar to what one expect from lower mantle inclusions. For instance, there's periclase and enstatite, and the conjecture was that that enstatite had been bridgemanite before. It transformed back into the chain silicate upon pressure release, but it remained in contact with periclase. Okay, so most of this work is done with, as I just had shown you, by polishing into these inclusions and examining with the SEM or with the electron microprobe, or people use Raman spectroscopy to identify phases. Now, the interesting issue is that actually such assemblies can also form in the upper mantle under conditions where there's lots of carbonate. So that's where diamond can form as well. So it's not really clear from these mineralogical findings from these paragenesis if they're really from the lower mantle, but they could. So many of these diamonds that Stachel and in particular Evan Smith are studying are very high quality. So I just show you again from a paper by Evan Smith some of these. This is so beautiful. And look at these sizes and look at their colors. So some of these diamonds here has a worth that is probably larger than the annual budget of my university. Now, of course, we cannot destroy such diamonds. So we have to study them as there is, and that limits pretty much what we can do with them. Much more information came actually from diamonds that are much less beautiful, such as this one here. This was published some 10 years ago by a group in Australia, where they believe to find evidence for hydrous ringodite inclusion in a diamond. Now that would be then direct evidence that this diamond comes from the transition zone. You have the transition zone mineral in the diamond and it contains water. And it's all based on Raman spectroscopy. Now, a few years after that, we went a step further by identifying with X-ray diffraction and spectroscopy inclusions of ice in diamonds. Now, this is not the formal normal phase of ice. It's actually a high pressure polymorph of ice, so-called I7. Ice has an enormous number of polymorphs. I think by now there's something like 14 or 15 polymorphs of ice. And much of their structural transformations are triggered by rearrangements of the hydrogen bond to denser packings. So this is normal ice down here. This is I7 here. So this is a cristobalite-like structure. So actually two cristobalite type lattices that are stacked into each other by translation along the space diagonal. And then the protons are arranging between the oxygens, still being hydrogen bonded. If you go to much higher pressure, actually I7 transforms continuously into an ionic bonded phase. So basically you have protons with a charge +1 and you have oxygen 2-, and there's no hydrogen bond anymore. So this collapse happens somewhere between 30 and 50 GPa, depending on the material. And this is a very ugly diamond. So here you see an intensity map of the diffraction pattern over this region in the diamond, and you see actually the locations of the I7 inclusion, and that diamond is just a chip from a larger diamond that we examine. So we have ice in the diamond. So again, that ties the water cycle with the carbon cycle in the Earth mantle, and it does it for a certain pressure, because this is a high pressure phase of ice. But what are the pressures? we went even further. So it's again an ugly diamond here. We made an X-ray fluorescence map. We find inclusions. You see actually here these cracks that are filled with siderite and calcite. And then you actually see up there, there's actually an inclusion that is not following these lineament here. So we examined that and we found that contains the so-called 10 angstrom phase. This is one of those dense hydrous magnesium silicate phases that form at elevated pressure, actually start dissolving aqueous fluid in magnesium silicate phases that are comparatively dense. And I will talk about this inclusion and the coexisting phases in a little bit. And then finally, last year, we reported with same type of techniques, the discovery of calcium silicate perovskite, dave-maoite. That was the one missing mineral of the lower mantle that was yet extant. It is very hard to stabilize it at ambient pressure. We could not find it anywhere else than in a diamond inclusion where the diamond sustains a sufficiently high stress on inclusion to prevent it from transforming back. So here's the diffraction pattern. Here's the infrared spectrum. This is the one of the laser ablation spectra that we collected, so we knew where the inclusion is. We drilled into the inclusion and determined its composition. So interesting aspects here are that this dave-maoite is fairly rich in potassium, and that actually again is consistent with formation at high pressure. So at pressures around 20 to 40 GPa, the ionic radii of potassium 1+ and calcium 2+ are nearly similar. So they both contract because under pressure, electron density increases. However, the electron density for potassium increases faster than that for potassium, and has to do with the transfer of 4s electrons to 3d electrons in potassium. So it's a pressure-driven effect. So it's a different chemistry from what we have at ambient pressure. Anyway, this high potassium content suggests that there's regional scale pathologic fractionation processes in the region where dave-maoite formed, because you need to fractionate potassium and enrich it high enough to actually form a mineral that contains that much. And we know from experiment that actually uranium and thorium are fairly well dissolvable in dave-maoite. So we basically concentrate all the three elements that have heat generating radioactive isotopes, potassium 40, uranium and thorium isotopes. So much of the radiogenic heat in the Earth mantle is coming from these three elements. And they are enriched in dave-maoite. So this is an interesting result as well. However, we need to understand at what pressure and temperature these diamonds formed and where did they entrap these inclusions of these minerals. And that's difficult. So previous work like that of Stachel and Pearson, they found potential retrograde products of high pressure minerals. Good. Then Pearson reported high pressure minerals that had survived to ambient pressure, that hydrous ring woodite that he reported. And now we have high pressure minerals that are still at high pressure, but they're at high pressure at 300 Kelvin. I have the diamond in my hand and it's at ambient pressure. And inside there's a tiny, tiny inclusion that is still at high stress because the diamond is stiff, has a high yield strength and extremely low elastic compliance. So it can actually sustain locally a high stress. So you have a diamond and it's in your hand, and inside the inclusions that are pressures like 5 or 10 gigapascal, so 50 or 100 kilobar. But it's at 300 Kelvin. So we can use this information now to reconstruct pressure temperature path. We basically just retract the path from the current pressure of the inclusion to the mantle geotherm. So this is what we did in the paper in Science on I7 in 2014. We just basically estimated with large tolerances for different inclusions where the path, the elastic path of I7 inclusions in the diamond would match the geotherm. So we we change the temperature and we see how the pressure changes. And if we hit the Mantle geotherm, we say, okay, so this kind of gives us an estimate of the pressure. So we see that some of them are from somewhere around 15 GPa, so that's kind of in the shallow transition zone. Some of them are from the lower Mantle. These dots here are an inclusion of ilmenite that we found, and that had a pressure of about 11 GPa at 300 Kelvin, and retracted that part as well. So now this is a Mantle geotherm, and we gave a broad envelope of plus minus 300 degrees here. Afterwards, we thought we could actually do this a little bit better. We can compare the elastic paths of different inclusions: ilmenite, I7, iron inclusions, periclase inclusions, whatever we find, and we retract those paths. And where those paths match, that should be then the depth where these inclusions have been embedded, if they had formed at the same depth. So the diamond formed and embedded these materials. It embedded ilmenite, iron, fluid water that then became ice. And so where those paths intersect, that should be then the pressure and the temperature where this diamond had formed. So we did this calculation. And so we came up with pretty high temperatures. They're below the peridotite solidus, but they're far above the current geotherm. Okay. So this elastic path calculation is close to isocores, just as a comment at the side, but actually what one really has to calculate is actually stress equilibrium between the diamond host and the inclusion locally. So it's actually, it's not a difficult calculation, but it's a bit tedious. So one needs fairly accurate thermoelastic parameters of all these materials here to do that. So, so we came up with those temperatures. Possible, a hot plume that passes through the mantle and traps those diamonds and carries them up, or reduces carbonate and generates diamond and traps those minerals. Fine. Although there's a few issues. I mean, usually at those temperatures in a mantle peridotite, carbon would be resorbed, so a diamond should not survive. But there's even a different issue, and it has to do with the fact that the diamonds that we have fairly high nitrogen content. They have a fairly high percentage of nitrogen that is bound in defects that are consistent with relatively low temperatures. So nitrogen is not very well compatible with the diamond lattice. Yeah, but it's entrapped when the diamond forms in the mantle. So it wants to get out. So over time, the nitrogens will be exhausted out of the diamond. But it's not a one-step process. It's actually a multi-step process. So the diamond first resides on a latticite plus an electron defect. It moves to a pair of nitrogens and a defect that's called the A-type defects. And it ultimately resembles into 4 nitrogen atoms on latticite that are surrounding one vacant cell. Those are called B defects. And then there are even more complicated arrangements of those B defects into two-dimensional clusters and so on. We don't need to discuss this. In any case, in 1990, people tried to come up with the calibration of the rates of these processes. So if I want to transform the A into the B defects, how long does it take? And at what temperature does this process become effective? So there's a correlation between the percentage of these type of defects and the nitrogen content. And this is just for one of those diamonds that I have. What we observe as percentage with some uncertainty and as a nitrogen content in that diamond, the temperature should not be as high as I had calculated here. In fact, it should be much, much lower. Or the residence time was very short. But you see, if you go from 1.6 million years to just 400 million years of mantle residence time, it does increase the temperature, but it doesn't increase it as much as I need to match those paths. So what's going on here? We're missing something here. And what we're missing here is the fact that actually even diamond becomes viscoelastic at mantle pressures, at temperatures somewhere above 1200 Kelvin in experiments. So on an experimental time scale, that implies it definitely becomes viscoelastic at Mantle temperatures on geologic timescale. And consistently, in many cases, the temperatures that we calculate from these nitrogen defects and these PT paths that we calculate for different inclusions match. So the PT paths intersect at that temperature. So the diamond might have entrapped these inclusions at much higher pressure, but we have no record of this because these diamonds and the inclusions have re-equilibrated in a viscoelastic regime until they switch, the diamond switched to a fully elastic regime somewhere below that temperature. And then these two paths split and we are in a fully elastic regime here. However, we also found some diamonds that have inclusions where the paths are not merging at the temperature that are obtained from the nitrogen defects. They're vastly different. So we came up with a simple scheme. We said basically, okay, below this temperature, we are in a fully elastic regime, and above this temperature, the diamond in the Earth has enough time to re-equilibrate with the surrounding mantle. So the mantle rock, the diamond, and the inclusions are all at the same pressures. So if we see a mismatch of PT paths at the temperature that we obtain from the nitrogen defect, we can take this delta P and we can take this delta T and calculate at what pressure the diamond, the inclusion had been entrapped in the diamond, just assuming that the PT path is going along the mantle adiabat. So that's what we did here. Those are two adiabats for mantle rock, peridotite, from this envelope of temperature uncertainty that we have. And we just take this delta pressure interval here, the minimal and the maximal interval, and then we came up with the PT conditions of entrapment. This is fairly rough, but it's still better than what we did before. If we do this, then actually our PT points are reset to reasonable temperatures. And they are above the wet carbonaceous solidus of mantle peridotite. They are somewhere around the wet solidus, and they're below the carbonaceous dry solidus, and they're far below the average mantle geotherm. Now that makes sense because these are diamonds that contain ice. So water was involved, and it's diamonds, so it's a carbon mineral. So carbon and water were involved. So basically matching these PT points with these experimentally determined solidi makes sense. And it's consistent again with this Rohrbach-Schmidt hypothesis of forming diamonds through dehydration of remnant carbonate and water in deeply subducted crust. Okay. We can even go one step further. We could actually take directly into account viscoelastic changes. We can basically calculate where the diamond would become viscoelastic at what pressure and temperature, and take our mantle adiabats from those pressures. So that actually brings us to somewhat higher pressures. If we do that, I cannot tell. These are rate-dependent processes, but these are rough estimates. And with either of the two approaches, we get into this regime of between the wet carbonaceous and the wet solidus of mantle peridotite at the pressures that we calculate. Fine. But interesting is that it also, the highest pressure point match the conditions where these dense hydrous magnesium silicates that I had mentioned before start to dehydrate from this pressure-driven transition of hydrogen bonds to an ionic proton-oxygen bond. So this, under these conditions, the water cannot be longer dissolved in mantle minerals, and it's dissolved as a fluid. So this process is experimentally determined to happen here, and this matches some of our highest pressure data points for diamond inclusions that contain ice, dave-marwite, and dense hydrous magnesium silicates. So is there a third water cycle? So in the Earth, a deep water cycle. So we have the surface water cycle that you all know about. We have the water cycle that is related to subduction and shallow release of water and island arc volcanism, which you also know all about. If there's still remnant water, which we see evidence for through these inclusions that we found in diamond, is there a third water cycle that's related to the dehydration of dense hydrous magnesium silicates into butchmanite, other oxides, and into fluid at those PT conditions. So then in subduction zones, most water is released at shallow depth. Below 410 kilometer, residual water that is still in the subducted lithosphere is no longer causing partial melting, but it reacts with magnesium silicates and enters those dense hydrous magnesium silicates like the 10 angstrom phase, phase D, phase B, the so-called alphabet phases. Because of the pressure-induced weakening of the hydrogen bond, these dense hydrous magnesium silicate minerals become unstable relative to ionic H2O fluid and dry silicates at high enough pressure. And this happens somewhere around 662,000 kilometer depth. This fluid then reacts with iron and iron carbide that has formed through the pressure-induced disproportionation of ferrous iron into ferric iron and metallic iron. And ultimately, there's diamond formation. And this is those highest pressure diamonds that we are seeing. Here's some more geochemistry. This is actually a diamond that contains the 10 angstrom phase. It also contains a garnet, so we can actually check our PT estimates by comparing it with geobarometry from garnet, and it matches. So the lower pressure from garnet geobarometry matches the intersection of the PT path of an ilmenite that coexists with the garnet and the temperature derived from the nitrogen defects. And that brings us to pressure temperature conditions at the release of carbonatite from subducted morph, and as well as from a little bit lower than from subducted lithosphere. And this inclusion was large enough to obtain actually trace elements, and we found that actually the composition of this inclusion is fairly close to what would be a source for the so-called high mu component. So a very radiogenic component that is found in plume-derived igneous rocks, particularly in ocean island basalts. So there's a paper about that here if you are interested in this. And it's quite different from diamonds that come from shallower depth or from maybe great depth, but from very particular environments such as the diamonds that Thomas Stachel and had examined. So we are actually fairly close to high mu source composition here, we claim. So this is then consistent with this hypothesis that Berkovitsky and Shunkarato came up with. So you have this decompression, dehydration and melt layer at the border between the transition zone and the deep upper mantle. And so this is exactly these PT conditions here. And this region then is enriched in incompatible elements, potentially radiogenic, and it causes at least some of the OIB that we observe, or at least its affects plumes that are coming from greater depth that are passing through this layer, because this is enriched, so it's overprinting anything that comes from greater depth. Then I7 bearing diamonds are either from within the transition zone or they form somewhere between a transition zone lower mantle boundary and maybe even up to about 900 kilometer depth inside the transition zone. They are forming at above the wet carbonaceous peridotite solidus, and they match the breakdown reaction path for dense hydrous magnesium silicate. So there's a lots of assumptions in these PT modeling here that need still experimental verification. We need more statistics. We just need more diamonds with inclusions from great depth to come to a better statistics and see if we can basically really match this decomposition boundary here. But I think with this kind of methodology here, we are moving towards a quantitative picture of lower mantle petrology. And so with this, I'm closing my talk here, and ask me questions. Thank you.
Oliver, thank you very much. It was a very impressive talk. ¿Alguien tiene preguntas aquí? o en el chat o en Facebook.
En Facebook no hay preguntas todavía.
I do have a question.
Okay.
A lot of people come up with a question. Is one of your first slides, you presented basically that the Earth has two main reservoirs of water. One at the basically at the crust, and the other one at the mantle. I think that's slide number 8. I think it was. Yeah, that one.
Mm-hmm.
Can you tell whether there is a exchange between the different reservoirs of water, and if so, how much is it? How much is that exchange occurring?
Yeah, thank you. This is a very good question. So first of all, there is exchange here. So the water that is in the transition zone is brought in there through subduction processes. So not all the water that is released during subduction and forms island arcs is it's not the entire water budget of the subducted lithosphere and crust. Some of that actually goes down into the transition zone, and there it's chemically dissolved. So now the big question is this is kind of a steady process of enriching the transition zone over time, and the water will stay there, and we eventually end up with a dry surface, or is this basically a cycle where water is also released? Now, this model here suggests that this is a cycle. So whenever there is an upwelling processes from greater depth, this water is released and generates volcanism. So that had been ardently debated. However, this inclusion that I just showed you here, and that's just one, yeah. Here, this is consistent with this. So we basically see a diamond that contains hydrous phases, and the trace element composition of this inclusion match that of at least a part of the OIBs. Yeah, so there's material that comes from that depth that is water rich, and that is involved in igneous processes that basically bring back material and water to the surface. But I don't think we can tell right now whether we have actually an equilibrium process or whether there is actually a net change in the balance of water between deep mantle and the surface over time.
So that would probably imply, therefore, that probably those two reservoirs have different origin, perhaps, and that could probably go into those theories of the origin of water into the planet.
Yeah, that's right. I mean, one would expect that there might be one can tell thermodynamically there would be a different oxygen isotopy for chemically bound deep water. It would be enriched in light oxygen isotopes relative to the heavier ones. Yeah. However, this is going through so many transitions when it moves from here to there that maybe such a signature is hard to catch. I mean, the one thing that we are looking for now would be an inclusion that is sufficiently rich in siderophile elements that we maybe can obtain osmium isotope data. Yeah.
Yeah.
That would, so that we basically could kind of tie time with enrichment of oxidation of rhenium and osmium to these processes.
All right, excellent. ¿Alguien tiene alguna otra pregunta? En Facebook o en el Zoom.
En Facebook todavía no tenemos preguntas.
Todavía no tenemos preguntas.
Ah, ya. Sí. Está en español. ¿Cuántos millones de años tarda el agua de las placas oceánicas en llegar a los reservorios del manto? Dice, how many million years does the water from the oceanic plates takes to get into the Mantle reservoirs?
Yeah, we do not have, so if you talk about this deep reservoir here, right? So we do not really have a good time estimate, which would have to come from isotope data. So these inclusions are very small, so you have to decide whether you actually try to hunt for isotope data, or if you want a bulk composition and trace elements. So you have to make the decision. There's not enough material for both of that, except perhaps for osmium. But we can get an estimate based on this this process here, yeah. So we basically get a trajectory of time and temperature. So if I take those temperatures, I get times, and they're fairly low. So these are basically timelines, and they're very rough. Yeah, these are very rough estimates, somewhere between a few 100 million years to less than 1 billion years. So centered somewhere around between 100 and 400 million years. So relatively short time scale for diamond. Yeah.
Thank you.
Otra pregunta. I do have another question. No one's jumping in. I think I missed it, but how big or how small are these inclusions? I mean, I gather that they're pretty small, but are these micrometer, nanometer?
So this scale here is actually in micrometer. So actually the Dave Marwhite inclusion is this one here. So this, and you can see that also here in the depth profile, yeah. So although this is actually in ablation time, it's not the micrometer, but there this inclusion is in the range of 5 to 10 micrometer in diameter. No? And it actually was platy. It's slightly elongated, but that's about the dimension.
And a more practical question is, how do you actually find them? Do you just looking at the microscope to several diamonds, or how you actually start getting find these inclusions? Or is just any diamond good enough for this?
That's also a very good question. Two questions, right? So to answer, how do I find it? It's actually mostly through X-ray fluorescence. Yeah, so with the synchrotron X-ray fluorescence, we have a spatial resolution, usually in the micron range. We can actually cut it down to 100 nanometer if you want spatial resolution. So the beam is focused into the diamond, but in a Gaussian beam path. So it's actually not really like a tight focusing like with the optical microscope, but it's more like a quasi-parallel beam that is as narrow as a micron or 100 nanometer. And it's basically exciting X-ray fluorescence throughout the diamond. Now, of course, some elements like this is a calcium K alpha radiation. The attenuation in a diamond matrix is fairly substantial. So we can only see it at depth of about less than 100 micron. Yeah, if it's very deep inside the diamond, you won't see it anymore. But we can see iron, chromium, nickel, titanium. We can see throughout the diamond. So we see those inclusions based on X-ray fluorescence. And then we collect with the same synchrotron X-ray beam, we collect diffraction data. So we know roughly what kind of elements are occurring in an inclusion, and then we know the diffraction data. And then we see if it's something interesting, an inclusion that is at a high pressure, say an ilmenite inclusion that is at 10 gigapascal, then we try to chemically analyze it with laser ablation, ICP-MS.
Okay.
Then what type of diamonds are this? Is this many diamonds? So we do not have a good statistics. Until I started this work, the general belief was that there's only very few diamonds that have high pressure inclusions that are usually back transformed. And these are type 2 diamonds, so diamonds that have no nitrogen anymore. The nitrogen have been exsolved over a long time, and they only occur at a few locations, like in Brazil and Guyana. There's 2 localities, and then perhaps in South Africa. So then we came and we have those diamonds that have high nitrogen content, so they had relatively low residence time, not a billion or 2 billion years, but maybe only a few 100 million years in the mantle, and they had formed at relatively low temperatures, far below the geotherm, and they contain those high pressure inclusions. We do not really have, as of yet, a good understanding where they occur. In general, we found localities in South Africa, in Brazil, but not where Thomas Stachel worked, actually Minas Gerais, Diamantina locality. We found high pressure inclusions and potentially in Angola. So it seems it's maybe a small fraction of diamonds that have inclusions that come from great depth. Most diamonds form in the shallow lithosphere, yeah, just at the graphite diamond boundary. 150 kilometer depth, yeah, and that's where most of diamonds form. There's only very few that we retrieve that form at greater depth. Inclusions that are still from the deep mantle have to be carried in diamonds over a relatively short time, geologically short time, and at low temperature. Otherwise, it would transform back. So if the temperature is too high, if you go along the average geotherm, the diamond would be viscoelastic, and at each pressure, the inclusion would transform into the phase that is stable at that pressure. So Dave Mauer would transform into bryite and then eventually into wollastonite.
Okay.
And then we have no record. So finding this, we need to look for diamonds that had formed at low temperature and had remained at low temperature for most of their life.
Okay. All right. ¿Alguna otra pregunta? ¿Alguien? Facebook, Zoom, ¿no?
Sí.
Una on Facebook. Okay, I don't have Facebook here. If you can.
Yes, there is another question in Facebook. I didn't understand in which form is the water in the wet layers. It is bounded to hydrous phases, or it is free in the mantle?
So generally, it is bound to hydrous phases, such as this one here. So so it's basically a hydroxyl group in a dense magnesium silicate. So basically, this material, 10 angstrom phase, is like talc. Actually, it's more like a phlogopite that is packed with water. However, when you start forming the diamond and you see free ice, you have to form a free fluid, right? So the formation of the diamond is related to the release of the fluid. So a free aqueous fluid phase, and that's then entrapped in the growing diamond. So both processes occur, but I think the diamond formation processes is already at the end of the residence of this material in the mantle. It's through an anomaly or perturbance of the material. So usually, if the let's see, yeah, if the material, the water is in the mantle, it's probably chemically bound. No? Yeah, so I think this term melt layer may not be taken too rigidly here. No? Yeah, I mean, seismologists have big issues with this. As you said, would not be stable. Yeah, but it could be that you have maybe a small amount of fluid or fluid-rich melt that is kind of penetrating grain boundaries here. No? We don't really know that well.
Okay. There's a question here in the auditorium.
What is the principal characteristic of that define a diamond of high pressure?
Did you hear that?
No, if you don't mind repeating it.
What is the main characteristic that defines a high pressure diamond?
Yeah, so in the past, we believed it's diamonds that have very low nitrogen content, or even those boron-rich blue diamonds. So those diamonds that I have examined are not falling in that category. They basically look very similar to lithospheric diamonds, yeah. So we do not really have a good characteristic for it, except through their inclusions. Generally, the diamonds that I examine have very few inclusions. So this is several hundred micron area here, and you see something like 5 inclusions, yeah? So this is very poor. So if you have a lithospheric diamond, you would usually see much more inclusion. So that's pretty much the only criterion that we have right now, is that these are diamonds that have a small amount of inclusions. In many cases, these diamonds are overgrown, so they have corners that are octahedral or dodecahedral in shape, and they're then either still dodecahedral or they're overgrown by some diamond that formed in the lithosphere. So as of yet, we do not really have a good criterion for identifying this particular type of high pressure diamonds that we look at.
Okay. Any other question? Facebook, Zoom? Well, I think that with that, Oliver, I want to thank you for your very interesting talk. Thank you for sharing this with us, and really appreciate it.
Yeah, thank you for giving me the opportunity to talk to your department. And I enjoyed this. I hope the talk was not too technical. I look forward to seeing you here in Las Vegas again. You work with Matt, so please come again.
Yes, I will. I will. Thank you very much.
Great.
Muchas gracias a todos.
Okay.
Bye-bye. Thank you.
Gracias.
Bye.
Bye-bye.